Hello everyone. As part of solving the image classification problem by considering the fashion MNIST data that we already have pre-processed, now let us look at implementing the model training process. So far we have done the data partitioning, we have done the necessary data pre-processing, created the dataset data loader objects. We also have created the custom class which is MLP. So we have instantiated this class to create the model object. We later have defined the loss function which is the cross entropy loss and also created the optimizer object. We looked at one particular prediction by conducting one forward pass and also observed what its maximum value is and what its corresponding predicted label is. We understood that it's a misclassification since we have not essentially implemented the model training process, which we are going to conduct now. So we'll have to conduct multiple epochs. So I'm going to write an iterative for loop for epoch in range of 100. So this is an arbitrary value again. So this here could be another hyperparameter. I'm providing a value of 100 for now. So that is, we are conducting 100 different epochs in this whole exercise. For each epoch, we are going to iterate over the existing train loader object, which is a generator object, right? So iter and then train loader. So this here is going to generate pairs of X and Y. We are going to iterate over batches of X and Y data, each batch comprising of 128 number of images that we already have transformed into tensor objects. Okay. And the normalization also is applied on that. Cool. So for each of these X and Y data, we're now going to conduct a forward pass. Let's conduct a forward pass using the X data here. So whatever predictions that we are generating from our forward pass are nothing but the raw logit values. We are later going to make use of these raw predictions, apply softmax in order to derive what the predicted probabilities are. Later assess which of these possible values or which of these possible logit values or predicted probabilities have got a maximum value. Whatever the label associated with that maximum probability value is going to be my ypred. Okay, that's what we have thought about, but we're not implementing that yet. So we are now looking at computing the loss. So the loss here is going to be P loss. Within the parentheses, we are providing the logit values as is. We're not converting them to probabilities yet. Since the cross entropy loss function has got this implicit conversion to probabilities, so it implicitly applies this softmax activation to all of these logit values. So we'll also pass the y labels, whatever y data that we are observing. We are passing the actuals as well as predicted values while computing the loss. So here we have conducted the forward pass. Okay, here we have understood what the loss is. Now we'll implement the backward propagation as well. So in this step, we are doing backward propagation. So once the backward propagation is done, once all the gradients are computed, now you look at updating the weights and biases using step function. Update weights and biases in the complete network. Cool. So once the weights and biases are updated, we'll zero out all the gradients as a regular process. So once all the necessary steps are implemented, we now need to evaluate our model at the end of each epoch. So at the end of each epoch, I am planning to evaluate the model, which essentially means that I'm planning to compute what my validation accuracy is and what my test accuracy here is going to be at the end of each epoch. Okay. Evaluate is a new function that we need to create, which actually accepts two different arguments, one of which is model object as is. The other one could be the validation loader in our first case, the data loader object. In the second case, it's going to be the test loader object. Cool. So, but we have not defined this evaluate function yet. So let's define this evaluate function, and we are going to define two different parameters, model as well as test loader. So I'm just providing an arbitrary name test loader. This here could be validation loader whenever we execute this statement, and this here could be test loader whenever we execute this statement. Okay, so it's just the name of the parameter. You can change this to any other name that you prefer to have. Okay, so now for each of X and Y pairs that I deduce from the test loader here, which again is a generator object, right? So obviously I am going to make use of this model that we already have received as a parameter and execute the forward pass here. When executing the forward pass, providing X data within the parentheses, now I am getting the raw predictions here. So whatever raw predictions that I got if I am applying softmax on it, I'm going to generate the predicted probabilities. I'm also going to understand what my predicted label is by using torch.max function by providing the predicted probabilities that I have derived in the previous step. We have learned about this pretty much, right? Within each of these inner for loop, I am now looking at understanding how many of these observations are correctly classified. So the number of cases where pred labels is equivalent to the actual y's here. Take the sum of it. Now I'm taking a cumulative sum. Since this is in a for loop, I'm taking a cumulative sum and assign it to something called correct. So correct is equal to correct plus number of correctly classified points within each of these iterations that we are conducting. So let me initialize this new variable called correct to 0. Also initialize a new variable called total here. So total is going to be the total number of observations that we have evaluated. That is equivalent to number of images that we have processed in each of these iterations. So once we have completed the inner for loop, once we have completed the for loop, once we have exhausted all of the data, now we look at how many number of cases did we correctly classify of total observations that we have evaluated. So correct by total multiplied by 100 here is going to be nothing but the accuracy. I'm going to return the accuracy here. And that's it. This is my evaluate function. So evaluate, provide the model as well as the relevant data loader object so as to derive the associated accuracy. I'm calling it as validation accuracy and test accuracy respectively. Okay. But I am just missing out some points here, right? So within each epoch, we are conducting multiple iterations. So at the end of each epoch, we are now tracking validation accuracy as well as test accuracy, which is good. So instead of running 100 different iterations or 100 different epochs to be more precise, let me run only 3 epochs for now. Okay. Let me also provide TQDM notebook so as to understand the progress of it. So while it runs, we can necessarily capture all of this information in a resultant data frame. So I'm going to create an empty data frame here called result. So whatever we have captured, whatever validation accuracy, test accuracy that we have captured so far, I now can actually write it to a particular data frame. So pd.data frame. And within this subscripts, I can provide the epoch number, the validation accuracy, as well as test accuracy here. Okay. So I can concatenate this with the empty data frame that I have created right before beginning of the first epoch. So I am trying to concatenate this with the result data frame and assign it to result back so that I capture each and every epoch and its relevant validation and test accuracies here. Let me end this whole process and let me rerun right from this step so that the weights are reinitialized. And now we can go about renaming the column names. The first column name here is going to be epoch. Second column name could be the validation accuracy, and third one could be the test accuracy. Print out the result as well. So once the result is printed, now you also can come up with a figure and axis, or can also come up with a plot to be more precise. Using plt.subplots function, you create figure and axis objects. ax.plot on x-axis, now you can come up with epoch, and on y-axis you can have the validation accuracy. And obviously I can provide a label so as to indicate this belongs to validation set. Similarly, I can also present what my test accuracy is, but label should be test here. ax.legend is going to display the legend for me, and obviously plt.show is going to display the plot. But I would also want to set the x label. X label here is going to be epoch. Size of it, the font size of it is going to be 14, which is arbitrary again. I can also set the y label here. Y label here is going to be accuracy. That's all. So we now have the result data frame ready. So we clearly know the validation accuracy for epoch 1 was 35.05. Test accuracy was 34.96. But these are not numeric in nature. So I would have to include change this to dot item so as to reference the actual values. Not done in the past. So now I am correcting that particular statement so that now you have proper representation of validation and test accuracies for each of these epochs. So we clearly know the accuracy is increasing epoch after epoch. And the deviation that we are observing between validation and test accuracy also is not that significant. Okay, but we need to conduct like n number of epochs. So we cannot restrict ourselves to only 3 different epochs. We need to conduct this whole iterative process probably to 100 different epochs or more. Again, as I have mentioned to you earlier, number of epochs is going to be a hyperparameter always. So we always need to actually perform hyperparameter tuning so as to understand what could be the right value for number of epochs. We also have come up with a plot here. Okay, but this is not sufficient. The number of epochs that we have conducted is not sufficient. If we are updating this number of epochs from 3 to 100, it's going to take a lot of time. The processing or the model training process here is going to take a lot of time. So it's not worth to actually implement this process on CPUs. And that's when we need to push our relevant data and model objects onto GPUs and then do our model training process on GPUs so that the runtime will speed up. Overall runtime that we might end up with is significantly lower in when you are using GPUs over CPUs. So that's what we are going to discuss next. How do we retrofit this particular code to actually push our input data and different model parameters or model objects onto GPU and then do our model training process on GPU rather than on CPUs? Look at it here. I've not connected to GPU at all yet. I can change my runtime type and I can select T4 GPU. So it switches from CPU to TPU here. Sorry, CPU to GPU here. Okay. So that's what we are going to discuss in our next session. That's pretty much all I wanted to discuss with you in this session. And thanks for watching.